Good afternoon to everyone, and welcome to the concurrent section number 12 on green revolution, green economies, and other technologies. I'm Antonio Gerascitano, and I would like to thank you for, I think, the Italian Association of Energy Economists for this appreciated invitation. As well known, this month, the European Union leaders have agreed on a goal to cut greenhouse emissions by at least 55% by 2030, compared with 1990 levels, in order to reach climate neutrality in 2050. Therefore, green economies are the pillar for this revolution. Indeed, in this concurrent section, our speakers are going to illustrate their research activities on this topic. As reported in the program, there are 3 speakers. Therefore, in order to be on time with the scheduled program, each speaker has about 20-25 minutes for the presentation. At the end of the session, there will be a 5-10 minutes space for questions and answers eventually. So the audience can send the questions, writing them through the Q&A chat. In addition, we suggest to indicate also the name of the speaker in each questions. Moreover, the speakers can also use the Q&A chat to write and send questions among themselves. Let's start with the first speaker. It's my pleasure to introduce Maria Milusi from the Technical University of Crete. She earned a bachelor diploma in mathematics from the University of Patras in Greece and a Master of Science in Applied Mathematics in Engineering Sciences from the School of Production, Engineering and Management of the Technical University of Crete in Greece, where currently she is a PhD candidate. Among her research interests, we can find life cycle assessment and cycle economy. Therefore, she's going to present a work entitled Life Cycle Assessment and Eco-Design Alternatives of Solar Thermal Technologies for the Promotion of Circular Economy. Maria, the floor is yours. Thank you. Maria, can you share your presentation?
Maybe
okay.
Some problems of connection.
Maria, can you hear me? I think Maria has a problem with the internet connection. Maria? I think that we can switch with the second speaker in order to save the time for the section. Is better. Okay, Maria is okay, he's online.
I am not going to use my camera because we have a problem with the back. I can fix it, sorry. So let me share my screen. Sorry for keeping you waiting. Is it okay now?
Yes, we can see your presentation.
Oh, thank you. So, Hello, and I would like to thank the organizers for the presentation in this event, and mention that for this research, two university departments collaborated: the Chemical Engineering Department at the University of Western Macedonia and the School of Production Engineering and Management at the Technical University of Crete. Professor Suliotis, Professor Papaktimiou, and myself have evaluated two solar thermal technologies through circular economy perspective, applying life cycle assessment and eco-design principles. So the main scope of this study is to present an analysis of the economic and environmental profile of two types of solar thermal collectors that are commercially available in the market and most commonly used, flat plate and vacuum tube systems. All the obtained results identify the product's environmental hotspots and provide insights and drivers for optimized design based on the circular economy guidelines. So this presentation comprises the following. At first, definition and principles of circular economy. Next, we will examine how eco-design and life cycle assessment connect to the circular economy model. We will have an investigation of eco-design strategies along with a definition of methodological stages of life cycle assessment. Subsequently, the determination of the parameters in the techno-economic analysis. And next, we will present the software and the databases that were used in the study and the introduction of the main features of the studied solar thermal collectors, with the detailed results from their evaluation, giving in parallel the environmental and economic profile of the studied technologies with the proposed eco-design aspects for solar thermal systems, and finally the conclusions of the study. Circular economy refers to an economic model whose objective is to produce goods and services by limiting the consumption and waste of resources, as well as the production of waste. It is in rupture with the model of linear economy by proposing to transform waste into recycled raw materials for product design. This model fits directly into the framework of sustainable development, as it uses, among other things, the principles of green economy, industrial ecology, etc. The circular economy can be broken down into 7 complementary patterns of production and consumption, which, when combined, reinforce each other. At first, we have sustainable procurement, which is the development and the implementation of a responsible purchasing policy. Eco-design involves the process of reducing the environmental impacts of a product or service throughout its life cycle. Industrial and territorial ecology develops the search for eco-industrial synergies at the scale of a business area. The waste of another company can become the resources of another. Economics of functionality refers to a collaborative economy that favors use over possession and thus tends to sell services related to products rather than the products themselves. As for the responsibility consumption, explains a rational consumption and choice of products according to social and ecological criteria. Extending the duration of use through repair, reuse, and repurpose. And last but not least, recycling, which involves the treatment and recovery of the materials contained in collected waste. Of course, we have a lot of benefits. The first benefit of the circular economy is in the environmental sector, which gives it is the protection of the environment, reducing waste and the emissions of greenhouse gases, systematizing recycling, adding plant obsolescence, and allowing to decrease the dependence on importation of resources, raw materials, water, energy. Another huge benefit of the circular economy is that it stimulates innovation and boosts economic growth, and could in the long run enhance the competitiveness of national companies Measures such as waste prevention, eco-design and reuse could save European Union companies around 600 billion euros, which is equivalent to 8% of annual turnover. In addition, the circular economy creates jobs, around 508,000 jobs in the European Union alone, and enables people to save money, cutting unemployment and poverty, as well as reducing the social impacts of pollution and climate change. Eco-design, on the other hand, can be briefly summarized as an approach where environmental considerations are integrated into the product design and development, and these considerations are taken into account in the early stages of the design process. A life cycle analysis is therefore an indispensable tool of eco-design and essential to properly compare different options to be implemented within a circular economy philosophy. Renewable energy systems need to follow this approach and benefit from it by modifying their design properties. Otherwise, without an effective end-of-life management, they will inevitably undermine their sustainable status. As circular economy principles attempt to close the supply chain loop, eco-design and life cycle assessment are important and related tools that enable this perspective. Moving on to the eco-design strategies, from an environmental point of view, a conventional product design process can be improved upon by applying appropriate eco-design strategies. Eco-design strategies are generally targeted at reducing the depletion of primary resources and other types of environmental impact. Depending on the type of product and its environmental bottlenecks, some eco-design strategies may be more suitable than others. Here we can say about the reduction of the number of different materials and selection of the most appropriate ones, or the extension of a product's useful lifespan, designed for reuse or designed for recycling. A leading environmental assessment methodology is the life cycle assessment method, which is a systematic analytical process for assessing the environmental implications of systems or products from materials production through product manufacture, use, and end of life. The term life cycle refers to the total time period between the acquisition of an asset and the moment that it is either fully depreciated or discarded as waste or sold on the second-hand market. Regarding the methodological stages of LCA, at the first step, we give the definition of the goal and scope of the study, the selection of the functional unit and the system's boundaries. In the second step, the goal is to identify all inputs and outputs of the process tree. At the third step, the inputs and outputs from to the system boundaries are linked to environmental impacts. And at the last step, the results of the previous steps are interpreted and combined to make a more informative and sound decision. Regarding the techno-economic analysis, the first step is a pre-feasibility study of a solar project, is to define the solar energy potential of the region in which the solar systems will be installed. This serves as a planning tool to quantify the anticipated electricity production and plant costs. To start the calculations, the current software needs a set of various characteristics regarding the examined systems, such as number of occupants, occupancy rate, operating hours, and then the software estimates the energy needs for hot water supply. In our case, the energy needs were estimated to be 2,817 kilowatt hours per year, taking as granted a typical family house with 4 occupants, the 100% occupancy rate and 24 hours of operation. So, about in the softwares and databases, in order to evaluate the environmental and economic performance, we use the SIMA Pro, which is an accurate and science-based tool, which provides a high level of transparency. And the Eco Event database, which is integrated in SIMA Pro and gives unlimited access to all the life cycle inventory datasets. For the techno-economic assessment, we used the Red Screen Expert, which is the current version of the software that allows for the comprehensive identification, assessment, and optimization of the technical and financial viability of potential renewable energy, cogeneration, and energy efficiency projects. So let's have a more analytical view of the studied systems. First, we have examined the flat plate solar collector, which consists of the dark absorber, the transparent cover, and the heat transfer fluid and the water tank. The vacuum tube collector, on the other hand, consists of vacuum tube of glass containing copper tubes in their center. Vacuum tubes are easier to install because they are lightweight, compact, and can be transported to the roof individually. In addition, the pipes can be replaced separately if they are damaged, avoiding the need to replace the entire collector. They are more efficient and cost-effective than the flat plate collector, approximately 70% performance compared to 50%, and they cost almost 1.5 times higher. Both types of collector have a lifespan of over 15 years. For the evaluation of each studied solar thermal system, the methodological order followed comprises 2 steps. And in this slide, we can watch the findings of the first step, which is a detailed cradle-to-grave life cycle assessment of the selected energy systems conducted via SIMA Pro. So here we can observe the process network of the flat plate collector with different cutoffs. And something similar happens in the case of the evacuated tube collector. The results of the networks clearly show that the production stage of the collector component contributes the most important part of the environmental impacts in the life cycle for both studied systems, around 57% of all the total inflows and outflows. So the obtained results identify the product's environmental hotspot and provide insights and drivers for optimized design based on the circular economy guidelines. For the evaluation of the studied systems, we use the recipe midpoint impact assessment method. Midpoint indicators focus on simple environmental problems like climate change, terrestrial acidification, eutrophication, land use, etc. Here, the cumulative CO2 emissions over the whole life cycle of the solar systems are quite close, and the lowest value corresponds to the vacuum tube collector. But as we clearly see, the 2 systems exhibited similar environmental impacts in most categories, but the vacuum tube collector has the highest values in most cases. The second step of the evaluation was the techno-economic analysis of the solar thermal collectors. And here, this assessment was used for the quantification of the energy output and the economic income associated with each of the studied systems. For the financial analysis, we considered that the electricity price has been set to 0.15 euros per kilowatt hour, and the installation was funded by own means. Both selected solar thermal systems can be considered as high quality products, and their purchase cost for the vacuum tube collector is 1,300 euros, and is significantly higher than 900 of a flat plate collector. From the economic assessment, we assume that the economic viability of the 2 systems is obvious, with a simple payback period in the worst case being 3 2.6 years for the vacuum tube system. In this matrix, we have highlighted some technical features in order to provide insights and drivers on choosing the most appropriate technology from a financial point of view. For example, thermal losses coefficient refers to the different thermal losses suppression design followed in each system. This parameter is decreased for the vacuum tube collector, something that makes the current system unaffected by variations in ambient temperature. Another technical feature is a solar fraction that shows the annual coverage of hot water needs in a percentage, where the vacuum tube system has a higher value compared to the flat plate collector. Overall, the thermal losses do not play an important role for the energy outcome of the systems, because the flat plate collector provides slightly more energy per aperture area throughout the year due to the favorable weather conditions in Crete, and so the advantages thermal insulation and the ability to reach a high temperature of the vacuum tube system is not necessary. Keeping in mind the environmental hotspots combined with the financial outcomes derived from the previous evaluation, our future research will focus on exploring the feasibility of producing solar thermal systems from a circular economy perspective, integrating eco-design principles at an industrial level. Some insights are the following. Eco-design aspects for solar thermal systems focus in designs that allow the device to be disassembled, and in this way we have improvement on their recycling potential. Other improvements that can be achieved are, for example, to be designed to allow the absorber plate to be detached from the storage tank. Or the storage tank can be made of stainless steel, as steel and aluminum can be cleanly separated and reused. Recycling has been investigated because many types of solar thermal collectors for domestic applications consist of large amounts of metals. This means that these types of systems present high recycling potential. Therefore, the adoption of recycling offers considerable reduction in the environmental impact and more efficient utilization of resources than using primary materials. Finally, from the evaluation of the environmental energy and the economic profile of the studied solar thermal collectors, we can conclude that the production stage of the collector component contributed the most important part of the environmental impacts in the life cycle for both systems. In addition, the two technologies exhibited similar environmental burdens, but the vacuum tube collector has the highest values in most cases. Moreover, both collectors could cover more than half of the annual hot water needs for a family house with 4 occupants, with the flat plate collector being equally efficient compared to the vacuum tube system due to the favorable weather conditions in the selected installation location. Continuing, the economic viability for both technologies is secured, as the simple payback period estimated to be 2.6 and 3.6 years for the flat plate and vacuum tube system, respectively. From the above mentioned results, it is obvious that the selection of a flat plate system is rather mandatory for typical installations in Crete, while vacuum tube system could be selected for more demanding applications. Future research should focus on exploring the feasibility of producing the systems derived from the suggested eco-design scenarios at the manufacturer level and their affectations in the installation stage. Thank you for your attention.
Thank you, Maria, for your presentation. However, no questions in the chat box. No, we don't have questions. However, we have just appreciated the holistic evaluation of the energy and environmental profile of the most commonly used types of the solar thermal collectors. namely flat plate and vacuum tube systems. Indeed, life cycle assessment is an important method to evaluate the system from the cradle to the grave in order to choose the most appropriate technologies for optimized design based on the circular economy guidelines. Okay, let's continue with the second speaker. It's my pleasure to introduce Kentaro Kambe from the University of Tokyo, Japan. Kentaro Kambe is graduated from the School of Engineering of the University of Tokyo in 2019, and during this year, Kambe has contributed to present works on maintenance and operation costs on power transmission and distribution network in conferences which held in Japan. In this conference session, Kambe is going to present a work which is entitled Impact Assessment for design of a wheeling charge system on electricity transmission sector and high school sector with a technology selection model. I'll give the floor to Kentaro. Thank you.
Okay, so can you see the slide?
Yeah.
Okay. Yeah. So, okay. Oh. Okay. Hello, everyone. My name is Kentaro Kambe from the University of Tokyo. Today, I will make a presentation on the following topics: impact assessment for right design of wheeling charge system on electricity transmission sector and household sector with a technology selection model. So today, this is today's contents. First, I will talk about introduction. First, in background. So Japan is currently moving toward a low carbon society, and the specific goal is to reduce CO2 emission by 80% by 2050 compared to 2030 levels. And recently, Prime Minister Suga has announced that Japan will achieve a net zero society by 2050. In order to achieve these goals, it is essential to massively introduce renewable energy and negative emission technologies. So, next, I introduce DAC and CCU. And DAC and CCU is one of the decarbonization technology of the future. Plant DAC and CCU are already being tested in Germany and other countries. And in theory, it is possible to use each home's air conditioner to perform DAC and CCU. But currently, no small devices have been developed to provide DAC and CCU at home. But in the future, it may be necessary to perform DAC and CCU in the household decarbonization. In this study, we assume that DAC and CCU have been realized in the household sector. So next, and one of the areas that create new problems in this context is the wheeling charge system. Wheeling charge is at the cost of covering the cost of transmission distribution equipment. And this accounts for 40% of electricity cost now. And the cost is distributed among the extra high, and low voltage low voltage, according to contracted power in the transmission and distribution equipment cost. The residential sector in this study is the low voltage sector. The right design of the wheeling charge is based on combination of energy-related and power-related components. Fixed costs account for 80% and variable costs are about 20%. On the other hand, the breakdown with commissioning revenue shows that the energy-related account 73% and the power-related account for 20%. This difference causes a problem that we will discuss in the next slide. The problem is under the recovery of transmission and distribution facility costs and the increase in the unit price of wheeling charge. The mechanism occurs as follows. First, PV and batteries will reduce the amount of electricity used by the grid. as a result, the possibility exists that transmission and distribution facility costs will not be recovered, and the unit price of the feeding charge will increase. As a result, disparity among the households will occur. So the purpose of this study is to evaluate the appropriate recovery of transmission and distribution facility costs due to the revision of the transmission tariff system, and to evaluate the impact of the revision on demand response technology, such as heat pump unit. The methodology of this study is based on the bottom-up technology selection model, which has been modified to consider the institutional design of the transmission tariff system and the consumption dynamics of the residential sector. Next, I will explain about method. First, the bottom-up technology selection model. The bottom-up technology selection model is a large-scale linear programming model with the objective function of minimizing the total energy system cost. Now, one of the features of the model is that it can evaluate the consumption dynamics, energy consumption, and CO2 emission of each energy consumption technologies. In this study, we have newly added transmission charge revenue to the objective function. Indeed, the residential sector will divide it into 100 categories. Next, I will explain about the objective function and the constraint. The objective function is the sum of equipment related cost, fuel import cost, and fuel domestic production cost, and the feeding charge cost. And the common constraint for the energy technology as shown in equation from 2 to 4. The supply-demand balance for all energy source and energy carrier as shown in equation 5. So next, I will explain one of the features of this study, which is the detailing the household sector. In this study, I divided the household sector in 100 different type households, and the load pattern of electricity and water heating demand is different for each household. And the installed PV capacity is optimized for each household. As for the generation pattern of the PV it is the same for all households. In this study, the installed capacity of the low voltage and the high voltage sectors are determined by optimization calculation. Next, I will discuss the DAC and CCU in the household sector. The entire energy system of DAC and methanation in the residential sector is shown figure, where the electricity and gas demand is given exogenously. Energy storage technologies such as battery are not considered within this stem. It is assumed that the heat required for the DAC will come from the exothermic reaction of the methanation. Therefore, the heat supply to the DAC is not considered. Indeed, it is necessary to be careful about the cost DAC. The cost of DAC is very low. Finally, I will explain the derivation of the feeding charge by iterative calculation, which is a feature of this research. The first step is to perform the optimization calculation as explained in section 2.2. Next, the optimization calculation results in the feeding charge revenue and the transmission and distribution cost. In the optimization calculation, the objective function includes the feeding charge revenue, but not includes the transmission and distribution facility cost. Third, perform the convergence judgment as shown in equation 6. If the convergence judgment is satisfied, then n times feeding charge is considered economical rational feeding charge. But if not, the unit price of the feeding charge shall be revised based on the cost of transmission and distribution facility and given as new unit price based on unit price of the feeding charge in the next calculation. Next, let's look at the result. First of all, Here's a case where the calculation is made under the current feeding charge system. The result of the optimization calculation is a defect and $760 million under the current system in Japan. Through repeated calculation, the result of modifying feeding charge are shown in table 3. From this result, it is clear that a large increase in the feeding charge will be necessary, and the cost of burden on normal household without PV will increase. The purpose of this study is to evaluate the reconciliation of the feeding charge system. In this slide, I will explain two types of case setting. The first one is the power-related component subject case. As shown in the figure on the right, and the breakdown of transmission and distribution facility cost is 80% fixed cost and 20% variable cost. Currently, recovery is done mainly through the energy related. This is thought to cause a problem. We will raise the recovery ratio in the power related to 80%. So this is the fixed case. Next is the case of the reviewing the contract laser recovery. Next is the case of reviewing the contract demand. As shown in the figure on the right, for PV installed household, the maximum transmission power is higher reverse tide than for forward tide. However, in the current situation, the forward tide is used as contract demand. This increase will require new investment, and which will require a new increase in transmission charge. Considering this point, the contract demand for the power-related components is set to the maximum value for the forward and reverse tide. These are the two basic cases. So once again, the case setting is as shown in table 4. BAU case is only repeated calculation, and CFA case repeated calculation and partial generation side bidding. And fixed case is repeated calculation and part repeated component subject case. And CFS and fixed case is repeated calculation and partial generation side bidding and part related component subject case. And the target year is 2050, and the target area is Tokyo metropolitan area, and the CO2 emission is net zero. The type of household in this study and their breakdown are shown in the table 5. So I will discuss about the effect of changing feeding charge. The figure on the left shows the comparison of the cost burden and equipment cost for each household in the BAU case. In the BAU case, households that use more electricity from the grid tend to bear more than the cost burden. Therefore, we can see that there is a cost burden gap between heat pump and PV and heat pump household. This cost sharing disparity has been best eliminated in the fixed and CFA case. In this case, the cost burden disparity problem has been solved by changing the contracted power, which is mainly basic and charge. Next, I will talk about the impact of the change in the feed-in tariff system on renewable energy technology. Figure 13 shows capacity of the DAC in the household in each case. From this figure, we know that by changing to a fixed case, the capacity of DAC will increase. And figure 40 shows installed capacity of PV for each household in each case. From this figure, the introduction of the partial generation side bidding system has the effect of reducing the amount of PV installed in the some household. So from this figure, although the cost burden disparity problem can be solved by changing the transmission rate system, it may inhibit the introduction of resistance PV and DAC. So next, we will discuss the energy supply and demand dynamics in the residential sector. Comparing the result in the left figure, the BAU case, and the methanation and DAC are only operating during the time when the PV is generating. On the other hand, in the fixed and CF case, the methanation is operating even at night. And this can be attributed to the fact that the electricity price per kilowatt has become cheaper since the feed-in tariff system. Which used to be mainly metered rate has become mainly basic rate. Finally, we will discuss CO2 emission and absorption. The figure on the left shows the amount of CO2 emitted and absorbed each sector in the BAU case. Most of the CO2 emission in the net zero case accounted for by the industrial sector and transportation sector. In the power generation sector, zero emissions are achieved. The change in the feed-in tariff has little effect on CO2 emissions. In addition, the degree of contribution of that in the residential sector to negative emission was little. Now, let's move on to the conclusion. In conclusion, we have developed a model based on the technology selection model that can evaluate feed-in charge and negative emission technology. And under the current feed-in charge system, it was found that the cost burden disparity problem will occur along with increase in feed-in charge. In order to solve this problem, it is necessary to change the feed-in charge system. And under the CO2 emission constraint, negative emission technology in the household sector will be introduced, but their contribution to the overall energy system will be small. And in the future, I will expand the target area to all of the Japan and consider other future technologies and services. So, thank you for listening.
Thank you for your presentation. Going to check in the box. No questions. Thank you for your presentation, Kentaro, on new technology selection model for analyzing the power in the household sector to assess the impact of alternatives wheeling charge system on each household under master residential PV deployment. Thank you very much again. Very interesting presentation. The last but not least speaker is Rocco D'Emilio. He earned a Master of Science degree in Industrial Engineering and Management from Polytechnic of Turin. Currently, he works as energy system modeler and analyst at E4SMA, namely Energy Engineering, Economic Environment Systems Modeling and Analysis, an Italian advisory firm. During his professional career, he has assumed senior expert roles in several projects, such as Horizon 2020 projects, entitled Delivering on the Paris Agreement, a demand-driven integrated assessment modeling approach, as well as project in promoting green economy in Kazakhstan and Central Asia for the development of a low-carbon economy. Moreover, he is a member of the Order of Engineers of Turin. For the 5th Energy Symposium, he is going to present a work entitled The Bridge Study, Belt and Road Initiative and Development of Green Economies, Challenges and Opportunities for the Green Bridge. Rocco, the floor is yours. Thank you.
Thank you very much for the introduction. I hope you can all hear my voice and see my presentation. Please just wave me in case you have any kind of problem. The study is about actually the Bridge and Road Initiative and was conducted in collaboration with my colleague Gabriele Cassetti and Xi Yang. And the first slide actually summarizes the entire work and actually serves as a kind of outline in a sense. So the study is inspired and partially supported by an ongoing European project, H2020 European project called Paris Rainforest, which actually aims to organize a collection of energy system models and general computer equilibrium models with the aim to investigate some kind of strategies to deep mitigation and reinforcing the Paris Agreement. This is basically the overall goal of the project. You can find some information about this project by navigating the websites. I have reported a link. But the study that I want to present is basically just kind of inspired by this project, and is mainly focused on the Belt and Road Initiative. Few highlights about this study is model-based in the sense that actually it involves two big energy system models, one for Central Asia and one for China. It aims to basically develop an analysis of scenario pathways for low emission economic development strategies in a geographical area which cover corridors from east to west, in a sense. It makes use of harmonized key supranational dimension and basic storylines, which basically means that models organize the story and the key components in a kind of harmonized way. At this stage of development, it aims to basically get some kind of insights from a comparative analysis between the two models. But in the future, the idea and the goal is to have a full integration of the two models. It aims to explore regional climate ambition versus the Belt and Road Initiative projects, and in particular the Belt and Road Initiative funds, and at the same time to unveil the trade-off between the potential of some of this area, in particular potential of renewable energy, versus the demand of this area, in particular the demand of energy. And as a final item of this outline, I would just like to say that one of the key research that actually we try to research question that we try to answer is whether the Belt and Road Initiative is a green project, which is a very controversial issue. But what actually we found out for the moment is that the Belt and Road Initiative calls for regulation and standard. It's not just about money to get a real green BRI. So I mentioned this acronym several times, but maybe it's worth to say and to spend a few words about what is actually the Belt and Road Initiative. It's actually a complex China transcontinental long-term policy and investment program, which actually was presented at the beginning of 2013. It involves the huge construction of infrastructure, and it implies the acceleration, at least ideally, the acceleration of the economic integration of the countries along the corridors, which are basically highlighted and designed in this map. In particular, in the corridor which is called Silk Road. So the corridor basically identified by these red arrows moving from the east to west. And when it comes to speak about energy and climate, the Belt and Road Initiative can also seen as a kind of, let's say, energy security issue for China, together with a lot of opportunities and risks for all the countries which are transit and which are somehow involved by this initiative. And we will try to unveil some of these opportunities and some of these risks in the course of this presentation. Now, the idea actually born by looking at the standard approach based on which this area of the world is basically considered in terms of geopolitics. What we wanted to do and what actually we theorized with my colleague Cassetti in a white paper called the Bridgeland Theory is that there's a trend to move from old-fashioned geopolitics, like, for example, this distinction between blocks, the heartland versus the rimland, into a more, let's say, connection-driven system, which we named Bridgeland. So basically, we moved from this kind of configuration of the blocks into a much more connected, let's say, block, which we call Bridgeland, which is not driven by let's say, political homogeneous entities, but more like a system of interconnected economies or a system of interconnected projects. And we then moved from this kind of description to a description which is much more model specific. So what we did was to collect from the modeling experience two models which pretty well cover this kind of new theorized Bridgeland, which are the model of China and the model of Central Asia. And we use this model to investigate the way the Belt and Road Initiative projects can affect on the climate and energy performance of these countries. In particular, the keywords of this integration are basically the standard ones: renewable energy, efficiency, plus hydrogen and trades, because the trades is one of the most important issue when we look at this part of the world. A few words about the models which actually we use to make this analysis. The first one is called MAPLE, is an energy system model which cover the Chinese system, is pretty much technology rich. It's capable to describe the entire energy chain from the upstream to the demand side. And in terms of analytical paradigm, actually is based on a dynamic least cost optimization, but is also linked with a computable general equilibrium model. So to basically take into consideration the responsiveness of the economic system in China. Of course, it tries to take into consideration the trades with the rest of the world, trades in terms of material, but in particular trades in terms of energy. The second model is called CAC, so it's the Central Asian and Caspian model, which explicitly represent 4 countries: Azerbaijan, Kazakhstan, Turkmenistan, and Uzbekistan. But implicitly, it represents also Kyrgyzstan and Tajikistan, so these 2 small countries at the border. The reason of this geographical coverage is that the time CAC was initially developed basically to access the deployment of the Caspian Sea Basin resources. So it was very much focused on the optimization of the upstream sector, and then was further developed to basically cover the entire energy system with a very, very rich description of the demand side, building, transportation, industry. It also has quite long-term horizon. Actually, both the model cover a medium to long-term horizon reaching 2050. It covers not only CO2 from combustion, but also the greenhouse gas emission, which are basically released in the upstream sector, which is particularly relevant in this case. And from the technical point of view, from the analytical point of view, this model belongs to the family of the dynamic partial equilibrium model and is formulated in mixed integer linear programming. So the way we approached the study was basically to, first of all, run the Chinese model, the so-called MAPLE model, in 3 different configurations. So we run a so-called reference, a business as usual scenario, an NDC, so a national determined contribution scenario for China, and basically inspired by the recent announcement of the very ambitious targets by 2060, we run a deep mitigation or nearly zero scenario for China. And you start to see here some of the results that we got from this exploration and the way China is capable basically to turn the curve of emission from an increasing trend to a decreasing trend. The very few highlights that I want to report here are that even in the case of nearly zero scenario, the electrification actually plays a significant role, of course, but is not basically the entire share of the final energy consumption. So it's basically around 50%. There is still some other energy forms in place. I have listened some other intervention during the workshop about the phase out of coal for China. And actually what we have experimented by running this model is that China can reach some sort of deep mitigation targets even without completely phasing out the coal. So you see that coal still plays some kind of role in the long term, even in the near zero scenario. Natural gas is mainly used to the power sector and not in the final energy consumption, which is also pretty much interesting as a finding because China has long-term contract with Turkmenistan, for example, for the supply of natural gas. And what we wanted to investigate, making use of this kind of comparative analysis, is exactly what kind of, let's say, synergies can be found between the Central Asian countries. Turkmenistan is part of the Central Asia and China. The final, let's say, comment that I have about this very high level overview of the results for China is that hydrogen and the hydrogen chain is triggered only when we simulate a deep mitigation strategy. So in the case of NDC, so in a kind of standard NDC representation, the target and the incentives are not sufficient to trigger the hydrogen chain. hydrogen is also one of the possible elements of integration with Central Asia, because due to the vast resources of natural gas in Central Asia, there must be the chance to basically reform natural gas, generate hydrogen, and export hydrogen to China. But what we see from this kind of first experiments is that hydrogen is projected to play a role just in the case of deep decarbonization of the Chinese system. Once we have learned from the Chinese exploration, we basically focus our attention on the Belt and Road Initiative per se. So what we did was to collect information about Belt and Road Initiative projects in Central Asia, and we basically come up with a list of projects divided by country and divided by sector. So you can see that the majority of the projects are in Kazakhstan, which is also geographically pretty obvious, because Kazakhstan is one of the largest countries in the world, and is a kind of natural transit for Chinese routes from east to west. So the majority of these investments are basically in Kazakhstan. Something in Uzbekistan as well, and just few investment in Turkmenistan, in particular in the gas sector, for the same reason I mentioned earlier, because basically there's an agreement between China and Turkmenistan for the supply of natural gas. No investments, we haven't spotted any investment in Azerbaijan, which basically means that so far the Belt and Road Initiative projects mainly look at the east part of the Caspian Sea and not at the west part of the Caspian Sea in a sense. We then tried to identify what kind of sector and what kind of projects these are. And we found out that there are some projects in the industrial sector, of course, mainly in heavy industry. So some kind of modernization or relocation of industry like iron and steel. Some projects about the transportation system, mainly in Kazakhstan again, which are basically mainly about the construction of railways, and some projects about agriculture and residential. But the capability of our modeling framework to represent this minor project was not very high, in particular because for residential was just about real estate and not something about energy. And as for agriculture, it was very hard to understand exactly what kind of project they had. So agriculture and residential were not considered in our analysis. Then projects about oil and gas, these are very much interesting because in fact are about modernization of refineries, modernization of secondary transformation processes, with the hope to, let's say, increase the efficiency of this sector, which is key in Central Asia. And as a final cluster of these projects, there are something about renewable energy, in particular in Kazakhstan, to basically promote renewable energy. The total of these projects ranges about $14–15 billion. And what we did with this kind of information, which actually corresponds, as I said, to a 5-year plan of China in Central Asia concerning the BRI projects, what we did was to take this information and to run our models in terms of optimization of the budget allocation for Central Asia. So once we know the allocation by country and the allocation by sector, since we have a very technology-rich description of the model, we decided to allocate this budget to the model to ask our model whether these kind of budget allocations are enough to trigger green changes in Central Asia. So this is basically the key question that we tried to answer. And to undertake this kind of analysis, we run the Central Asian model under different interpretation of the Belt and Road Initiative, and we benchmark this kind of scenarios with let's say, standard or basic scenario. So the first scenario is basically the current policy, where we have an evolution of the CAC systems, just take into consideration the existing policy and measure of the 4 explicit countries. Then we applied on top of the current policy the projects which are called BRI with the funds that I described before. And then we have run also some kind of sensitivity. So what if the project actually can let's say consider twice the value of the funds or 3 times the value of the funds. This is because generally the way China is thinking this kind of funds are based on 5 years plan. So the idea is to consider the first 5 years plans for 2020, the second 5 years plan for 2025, and the third 5 years plan for 2030, and see whether this kind of budget is at least sufficient to basically cover the ambition of the Central Asian country with respect to the NDC targets. And we will see whether this is actually correct or not. But to enlarge the comparison and to learn from this kind of comparison, we run also additional scenario for the Central Asia. So the NDC, as I said, a deep mitigation country specific and a deep mitigation synergic, meaning that the allocation quota was basically determined endogenously by the model instead of predetermined. Here you see we have reported some kind of extra cost of this scenario with respect to scenario 1, which gives an idea about the magnitude of the effort that this country has to make to turn their system from a current policy projection to something which is more green, and also to give a kind of magnitude of the value of the Belt and Road Initiative funds with respect to the extra cost. We talk about $14 billion, as I mentioned earlier, against $100 billion just in the case of the NDC. So we see from the very beginning that there's a kind of gap in terms of money first. To collect and organize our results and our findings, we prepare a dashboard. A dashboard is a kind of visualization platform which actually we use and share with local stakeholders to organize our findings and to discuss with them our findings, to iterate the process so that to maximize the capability of modelers our side, to collect and reframe our modeling exercise, and for the stakeholder to better understand the outcome. So actually we try to speak the same language. In this slide, what I've reported is basically the comparison between the current policy scenario for the entire Central Asia and the BRIC-related scenario for the entire Central Asia. So the finding is that apart from very minor difference in the middle of the time horizon, let's say from 2025 to 2035, the two pictures are very much similar. What is the meaning? The meaning is that the BRI in the original configuration, so the original set of funds, which are basically destinated to the Central Asia, are not enough to trigger long-term changes into the Central Asian system. The only benefit that they have is basically to flatten the emission profile instead of allowing this kind of further increase until 2030, 2035. So this is basically the only benefit that the standard BRI projects may have in the Central Asian system. But to enrich the description, what we did was to make a comparison, this time not only between the current policy scenario and the BRI scenario, but between the BRI scenario and the NDC scenario. So what is the gap between the current BRI and what is the optimal configuration under the NDC? Well, the gap is pretty much evident, for example, in this chart. There must be much more, let's say, space for renewable energy to reach the NDC target. This in particular is wind, which must be incentivized much more than it is now based on the funds of the BRI, and the same for solar PV. But it's also in the final consumption. This is about final consumption, and you can see that these two stacked columns are much shorter than these two stacked columns. What is the meaning? The meaning is that actually the NDC evolution would call for much more efficiency in the system, which is not sufficiently triggered by the funds of the BRI. This is a configuration about the entire Central Asia, but the dashboard and our analysis can also be turned into something which is country-specific. So what we did in this chart was just to select Kazakhstan instead of selecting the entire CAC package of country. And again, we run a kind of comparative analysis exercise. In this chart, now we have the standard BRI only for Kazakhstan, the NDC profile for Kazakhstan, and by looking at this kind of comparative exercise, we see that in the case of Kazakhstan only, which is the destination of the majority of the BRI funds, the two curves are very much similar. So what is the meaning in this case? The meaning is that the BRI project in Kazakhstan, because of their amount and because of the target they have in particular for renewable energy, are capable to turn the system into something similar to the evolution which is expected by the NDC. And you can see also this phenomenon from here. The two parts of the charts are very much similar, meaning that actually the BRI perform in a similar fashion as the optimal NDC scenario, which is very good. But what we did was also to try to enhance the BRI, as I said, as a kind of sensitivity analysis. So what happens if actually the funds for the BRI are basically available in much larger amounts, so 3 times bigger? Well, what happens is that this slope for the greenhouse gas reduction trend is much more evident now. And you see even from here that the capability of the system to generate renewable energy should be incentivized much more in this case. What we did was also to basically make a comparison of the standard BRI and the enhanced BRI with a deep mitigation scenario for Kazakhstan. This is just to learn what kind of project the BRI must finance to turn into a green initiative. And this is a kind of comparative exercise which is very much important. In the between of the charts, now we have the deep mitigation scenario. Here we have the enhanced BRI, and here we have the standard BRI. And the gap is very much evident about renewable energy. So if the BRI aims to be a green initiative, must trigger much more the renewable energy rather than the current situation. And also must play quite a lot in the energy efficiency side, because again, in a comparative manner, we can say that even the enhanced BRI generates a projection of consumption which is significantly higher than the consumption that would be needed in case of a deep mitigation for Kazakhstan. So BRI has some potential, but if the idea is to turn into something green, and if the idea is to compare the potential of the BRI against deep mitigation scenario, there is still quite a lot of work to do. A few conclusions about this work. The BRI is definitely a huge opportunity for the region, but the impact is kind of controversial because it depends on the way the budget is used and the amount of the budget, which is still quite uncertain. So far, what we have spotted is that the existing projects mainly have an effect in the short term without actually being able to keep this kind of long-lasting impacts on the CAC region. There's a risk of stagnation of the BRI in the Central Asia. Let me just spend a few words on this point, because China sees the BRI and the investments in Central Asia even as an opportunity to relocate or to transfer some of the heavy industry from China to the Central Asian area, which might have a kind of rebound effect in terms of consumption, in terms of emission. The two main, let's say, weaknesses of the BRI so far in Central Asia are the fact that the BRI does not cover the building sector, which is one of the most important sectors due to the heating demand in Central Asia. So no gain actually can be, let's say, expected by the building sector with the current configuration of the BRI. And is not covering the private transportation, which is also pretty much important. So it's not bringing any, let's say, regulation or framework or standard, which actually may enable the private transportation to play a role in this kind of climate mitigation. As a final comment about this specific issue about BRI, is that, of course, the impacts are different if we look at the entire CAC region or if we look at just country-specific information like the case of Kazakhstan, where the current project, in particular the investment in renewable energy, have some minor positive effect already with the current budget. Few words about the next steps. The idea is basically to have the model available for engaging stakeholders in new analysis of BRI, new interpretation, much deeper, let's say, dive into the project of the BRI that China is expected to propose for the future. And the idea is also to include directly China in the dashboard, so to engage the stakeholder of China the same way we are working with the Central Asian stakeholders, making use of a tool which is very participatory and very easy to use. And from the point of view of the methodology or the topic of research that we would like to further explore, we are on track a paper about hydrogen and the way hydrogen is built, is created in Central Asia and is transferred to China. And this kind of study can be coupled with, of course, any kind of study about Asia near zero emission future, and which is the most relevant one, in my opinion, something about the CDA. The CDA mechanism is the cross-border adjustments, which is very much important when we want to consider the impact on some kind of industrial projects and the way the heavy industry will have to evolve in order to keep some kind of minimum level of productivity in the market. So thank you very much for your attention. You can find here some references, and I'm now ready for any question, just in case you have questions. Thank you.
Thank you, Rocco, for your presentation. Any questions from the floor? Also from our attendees, speakers? In any case, we have appreciate this project on a Green Belt on Road initiative, which advocates a low carbon, circular and sustainable development. Indeed, this result may support policymakers and all stakeholders. No questions? Thank you to our speakers for their contributions, all attendees. Have a nice continuation of the virtual conference. Thank you.
Thank you all. Bye.
Bye.
Thank you so much, and see you tomorrow at 9.
See you.
Thank you. Bye.
Goodbye. Have a nice day.
Have a nice day. Bye.
Have a nice evening.